So in this unit, we're going to learn about work, power, and mechanical energy. So work is something that we do on an object when we transfer energy to that object. And according to the law of conservation of energy, which we're going to talk about further in topic 2, energy can be neither created nor destroyed. It can only change forms. So work is the way in which we transfer energy. So work is actually just equivalent to energy, and that is called the work-energy theorem. Now, so to kind of put this in perspective for the entire semester, we have that energy is expended in the form of work, and work is accomplished by applying a force to an object, and when we apply force to an object, we cause that object to move. So we started in the first unit talking about observing motion, and then we learned about why things moved, and now we're working our way backwards here, and we're looking at the energy and the work aspect of it. So I'm going to start by talking just about work. So work is done if you apply force for a specific amount of distance. And so the equation for work is that work is equivalent to the force times distance. Now there's this sign here that stands for parallel. So the only force that contributes to work is parallel to the distance or the displacement of the motion of the object. So if you're given, if you're pushing an object like a shopping cart or a lawnmower, typically you're pushing at an angle. So if you're given some sort of angle, then we take the cosine of that angle just to get the x component or the component that's parallel to the displacement, and use that to calculate work. So let's go ahead and just do a couple of sample problems, and then we'll talk about the units. So this is the problems that I have here, and let me get the Elmo pulled up over here, and I'll try and, oh, I don't think I can expand that window, so let's just go ahead and make it a full screen. Alright, so let's say that we have a book on a table, right, and the book is 2 kilograms. And we are going to push the book with a force of 10 newtons, and we move the book from one location to another, and when we get it over here, let's say we've just moved it like, I don't know, 1.5 meters. So this is a very simple problem. If we were trying to calculate the work, we would say work is equal to force times distance. So the force that I apply is 10 newtons. The distance that the book moved was 1.5 meters, so I get that the magnitude or the quantity of work is 15. So what is the unit? If we look at the unit here, you see force is in newtons and distance is in meters. So this is newton meters. Now that looks pretty similar to what we learned when we learned about torque. But remember that we had this symbol there. Torque is the force parallel to the distance from the point of rotation. So this is very different than torque. Now, we know that work is equivalent to energy. So the Newton meter, actually we give it a name to distinguish from torque. So Newton meters are also referred to as joules, which is the unit for energy and work, which we write with the letter J. So typically you'll see, instead of Newton meters for work, you'll see J for joules. Now let's go ahead and look at an example where we're at an angle, right? So let's say we have that shopping cart example, and you're pushing at an angle of, I don't know, let's say this is 30 degrees. And we take this object and we push into the handle with, I don't know, 50 newtons. And let's say we move the shopping cart a distance of 5 meters. Okay, so remember that the only force that contributes to the work is the force parallel. So we would be dealing with this component because this x component would be parallel to the displacement. And if you notice, this would be the adjacent, so that's why we would take the cosine of 30. So remember the equation was FD cosine of theta. So we're just going to take 50 times 5 times the cosine of 30. Right, and let's punch that into our calculator. 50 times 5 times the cosine of 30, and I get 216.5 joules. So 216.5. joules.